Hello, our dear viewers. Previously on our discussion about rotational motion, we have tried to see about rotational kinematics, rotational dynamics, rotational work, energy and power, and at last we have tried to see about rotational or angular momentum. And today we'll try to see about a new unit, and that is equilibrium. We'll try to see about mechanical equilibrium. There might be different equilibriums like chemical equilibrium and so on. But here we emphasize on mechanical equilibrium. Under these units, in unit 7, which is equilibrium, after the end of this unit, you are able to define what does it mean by equilibrium. And you'll able to the different types of equilibrium. You are able to see the types of equilibrium as well as the different conditions of equilibrium. We can classify the objects that we are trying to deal as rigid body and particle system, and you'll try to apply those conditions on these two systems. And you are able to have a basic concept and skills in solving equilibrium problems. Okay? Then let's start with the definition as obvious. What do you mean by equilibrium, or what is equilibrium? Well, equilibrium in physics can be considered as the term which expresses or tells us conditions of equilibrium or conditions of state of balance of a given structure. It is the measure of state of balance of a given structure. There might be a bridge given, and that bridge should be in a state of balance. That means the net force exerted on that object should be balanced so that it has a proper function. If you have a building, that building should be in a state of balance or in a state of equilibrium for it to properly function. Unless if that system is not in a state of equilibrium or balance, it will be collapsed. Therefore, this is what we call equilibrium. Equilibrium is a measure of state of balance. There are basically two types of equilibrium that we are going to deal, and these types of equilibrium are known to be static equilibrium and dynamic equilibrium. Static equilibrium is equilibrium exerted on a given stationary body, and that object has net force, and the net force exerted on that object is due to its stationary. In your dynamics concept, or you have learned it in unit 4, the net force on a given object is 0 only if the two objects or the object is at rest or either the object is in a state of motion with constant velocity. If it has a constant velocity, the net force on a given object can be 0. Or if the object is at rest, or if the object has 0 velocity, the net force on a given object is 0. Therefore, static equilibrium tries to study or emphasize on a given object at rest. That means the object has 0 velocity. Whereas in dynamic equilibrium, the object has a uniform motion, but still the net force can be 0. The net force on that object is 0, but that is 0 because of the velocity is constant. But in this case, in static equilibrium, the net force is 0. The net force is 0 because the velocity of the object is 0. That means the object is at rest. So in this unit, we are trying to deal only on static equilibrium. At some other level, might be in engineering, you might see about dynamic equilibrium. So let's try to see about static equilibrium. And the other point that we have emphasis on is the objects that we are going to study. There are different structures or objects to be studied, and these objects might be categorized into two, as particle system, or might say point mass system, or sometimes you can say mass string system, not mass spring, mass string or rope system. And rigid body system, these other bodies that we are to focus on, like you might have a bridge, you might have a bar, you might have a cantilever, or different structures, so that we can focus on rigid bodies, and we can see also on particles system. So these are the structures that we are going to deal. And the very basic concept here is the conditions of equilibrium on those objects. For stationary bodies, for either particle systems or rigid body system, what are the conditions for those objects to be in a state of equilibrium? Well, we have two conditions of equilibrium. The first condition is known to be translational or a linear condition. The other condition is known to be a rotational condition or angular condition. So, the summation of the first condition states that the first condition of equilibrium is known to be translational condition or a linear condition. And it states that on a given structure, whether it is a particle system or rigid body system, the net force exerted on that object should be zero. Okay? The net force should be zero is the translational conditions of equilibrium. That means when we mean by net force on a given object, different force might be exerted along the x-axis, it might be acted along the y-axis and along the z-axis. But we mainly focus here on the two dimensions, on the x and y-axis. So the net force exerted on the x-axis and on the y-axis must be zero. And the net force on the z-axis is by default zero because we are trying to deal only on two-dimensional objects. But at higher level, you might see about the third dimension. So we are trying to mainly deal about the net force exerted on the x-axis and on the y-axis should be zero. That should be the technique that we are trying to focus on. And the second condition of equilibrium is on a given body, the net torque must be zero. The equivalent representations of force for rotating objects is torque. We have already dealt on the angular motion on a previous unit. So the net torque on a given object must be zero. The net torque must be zero. That means the net torque is the summation of torque, counterclockwise or anti-clockwise, plus the summation of net torque clockwise must be zero. That is the case. But for sign convention, we know that the net torque acting clockwise can be considered as negative, whereas counterclockwise or acting anti-clockwise can be considered as positive. So this is negative or minus. You can negative here. The net torque acting counterclockwise minus clockwise torque is negative minus the summation of torque clockwise is zero. Therefore, when we transfer this to the other side, we can possibly say that the summation of torque clockwise is equals to the summation of torque counterclockwise or anti-clockwise. So this is the second condition, or known to be rotational conditions of equilibrium, whereas the net force must be zero is the first conditions of equilibrium. So far, we have tried to see the two types of equilibrium, static and dynamic equilibrium. The other thing that we have seen is the systems that we study is particle system and the rigid body system. And now we have seen that there are two conditions of equilibrium. The first condition is known to be translational condition. The second condition is known to be rotational condition. For those systems, the particle systems and rigid body system, when we are trying to apply those conditions, which condition is appropriate for which system? We'll try to see that. For a point mass system or for a particle system, only first condition is enough to suffice state of balance. If the first condition is fulfilled, it's enough for objects to say, for such objects to say in equilibrium. So it says for a point mass or for particle system or mass string system, the first condition is enough. Okay, it's the only and sufficient conditions required for those objects to be in a state of equilibrium. It says sufficient conditions, okay, and it should be fulfilled. You don't need to use the second conditions of equilibrium for a point mass or for a particle system or for a mass string system. You don't need to use the second condition or rotational conditions of a system. But for a rigid body system, both conditions must be suffice, or both conditions must be fulfilled. That means the first conditions of equilibrium, the translational condition, and the second condition or rotational condition must be fulfilled. For a rigid body, both conditions, the first condition and the second condition must be fulfilled for it to be in equilibrium. In this case, we have a bridge. A bridge is a rigid body system. You might have a bar. a bar is a rigid body system. So on these objects, you should have to apply both conditions, the first condition and the second condition. So these are the theories. Now let's try to see examples. Here you have an object of mass 3 kilogram. Here you have 3 kilogram object, and it's attached with cords or strings as shown here. Hangs from 3 lights inextensible wires as shown in the figure below. 2 of the wires makes an angle theta 1 53 degree and theta 2 37 degree. Here theta 1 is 53 degree and theta 2 is 37 degree, meaning this is 90 degree, okay? Since it forms a triangle, okay? When you add these two is 90 and this is 90 as well, 180 degree. Then it says the system is in equilibrium. We are considering this system to be in equilibrium. And the question is, what are the tension exerted on each objects, on each strings, or on each cords, we can say that. This system is known to be a mass string system or a particle system. For a particle system, we have said that the first condition is enough to check whether these bodies are in a state of equilibrium or not. Actually, it's given that the system is in equilibrium. If so, we should have to check only the first condition. To check the first conditions of equilibrium in dynamics, you have learned that it's possible to use free body diagram. As well as in rotational dynamics, we have used free body diagrams for each. In this case, what are the force exerted on this object? The first force which is acting on this object is a weight. There is a downward force exerted due to the weight, which is mass times gravity. The mass of the object is 3, the gravity is 10 for calculation, so that there will be 30 Newton force exerted on this mass. While this amount of force is exerted downward, there should be a resisting force. There should be a force which tends to act oppositely, and that is the tension exerted on this string. Okay? Always on strings and ropes, there are 2 effects. The first thing, as this object is trying to pull downward, it will exert a force upward. Let's say that this is tension T. We can call it tension T. And the other thing is, if this rope is cut into half, this object will tend to move towards me. But it should be kept on that equilibrium position due to the tension formed here. Okay, let's call it to be tension T2. Suppose if you cut here, this object cannot stay in equilibrium. Why? If you carry it, it will move to that side. So the tension exerted here is kept it to be in equilibrium. Let's call it to be tension T1. And the other thing is, these 2 objects are pulled downward due to the tension exerted here. So here you have a tension, let's call it to be T2. Here you have tension T1, and there is a tension exerted T. And the tension T is also reacted upward due on this mass. Okay? On these 2 strings, it's acting downward, but on or against this mass, it's acting upward. Therefore, you should have to have the free body diagram of this and the other free body diagram of those tension T. We can put it on X, Y, Z like this. The free body diagram of the mass is acting downward mg. There will be an upward reaction force tension T. So when you are trying to apply the first conditions of equilibrium, it says the net force along X, along Y, and along Z are all must be 0. Actually, you don't focus on Z because it's always fulfilled. For any given questions in this level, the net force along Z must be fulfilled. So you are going to focus only on X dimension and Z direction. So there is no any force acting on this mass along the X-axis. The net force along the X-axis is 0. So your only focus should be the net force along the Y-axis must be 0. The net force which are acting here is, there is an upward force, tension, there is a downward force, the weight. In your dynamics concept, you have learned that the net force is equals to mass times acceleration. This was the concept. But here, we don't have acceleration. Either the object is at rest or the object is in a state of uniform motion. In this case, we are trying to deal on mass string system, and it is at rest. If the object is at rest, the acceleration is 0, so that it is what it says. The net force must be 0. And the net force exerted here is tension T and weight acting downward. So the tension is acting upward, the weight is acting downward, so tension minus mg should give us 0. But when you translate it to the other side, it gives you tension T is equals to the weight mg. So the tension is the weight itself. Previously, we have the tension here. It is 30 Newton weight. This is 30 Newton counterbalanced by the tension here. The tension itself should be 30 Newton. Why? This system is in equilibrium. For it to be in equilibrium, the two forces must be equal. So the tension is 30 Newton. The other thing that you should have to put it here at the junction, you should have to put all the force on x and y Cartesian coordinate system. So when you put it on xy system like this, you have y-axis and x-axis. The force that are acting here is T2 and T1. The angle here, this is 53 degree. When you put the axis here, this angle and this angle are alternate interior angles, okay, for two parallel sides, and here this angle and this angle are known to be alternate interior angles. If this is 53, this is also 53. If this angle is 37, this is also 37. Therefore, we can put it on xy plane like this. Theta 1 is 53, theta 2 is 37. And you can decompose those force components along the x-axis and y-axis. Should have to be on this way. So you should have to decompose all the force components along x and y. So the horizontal component of tension T2 along x can be given as T2 cos theta 2. T2 cos theta 2. And the horizontal component of tension T1 can be given as T1 cos theta 1. And the other thing is these two force has a vertical component. Okay? The vertical component of this force and the vertical component of this force can be given as T1 sine theta 1 and T2 sine theta 2. These are the two components, the vertical components. And at last, you have only components which are acting along the axis, and you have only force components which are acting along the x-axis. The first law of equilibrium states that the net force along the x-axis should be 0. The net force along the y-axis must be 0. The net force which are acting along the x-axis should be 0. What are the forces which are acting along the x-axis? Well, the net force which are acting along the x-axis are T1 acting along the x and T2 which is acting along the x. These are the horizontal components. And the upward components are T1 along the y-axis and T1 along the y-axis, T2 along the y-axis. These are acting along the same axis, so we can add these two. And the other force which is acting downward is the tension T. Previously on the diagram, we have a downward force exerted on this string. It's called tension T. Actually, we have already find it to be 30 Newton. So here we have 30 Newton and it's acting downward. The net force acting along the x-axis are T1 cos theta 1 and T2 cos theta 2. This should be balanced for it to be in equilibrium. You can put it like this. T1 cosine of theta 1 means theta 1 is 53 degree. Cos 53 is given to be 0.6. Cos 37 is given to be 0.8. So T1 can be given as 4 over 3. T2, we can rearrange and find an expression between tension 1 and tension 2. T1 can be expressed in terms of tension T2 as 4 over 3. Okay, later put it here. And the other concept is, when you apply the first conditions of equilibrium, the net force which are acting along the axis must also be 0, or it must be balanced. So what are the force acting along the axis? The upward force components, T1y and T2y, or T1 sine theta 1 and T2 sine theta 2 are acting upward, and the other force acting downward should be balanced. So T1 sine theta 1 plus T2 sine theta 2 is equals to 30, or the downward force is T. 0.8 T1 plus 0.6 T2 gives us 30. Then what? You can put T1 here and find an expression, or it's possible for having a relation for T2. T2 is 3 over 4. T1, you can put it here in terms of T2 and find an expression. And at last, we can find tension components T1 to be 24 Newton and T2 to be 18 Newton. Okay, T1 is 24 and T2 is 18. T1 is 24 Newton and T2 is 18 Newton. This is 24 Newton. It carries 24 Newton, and this one it carries 18 Newton, and this one it carries 13 Newton to balance this system. So this system is balanced due to the tension exerted on each cordus. This is how we solve a mass string system. On a mass string system, the first condition is enough. So far, we haven't seen the second conditions of equilibrium. Now let's proceed and try to see the other problems. Suppose here you have a bar, and on this bar, here you have a bar, and here you have a weight. Let's assume that the weight of this load is to be 200 Newton, and this mass is found at an angle of 53 degrees from horizontal. And here you have a string or a chain or something which holds this bar, and let's have it a tension T. On this string, we could have a tension T. Now the question is, a 100 Newton uniform bar, the bar itself has its own mass or its own weight. A 100 Newton uniform bar is supported by a cable. Here you have a cable as shown in the figure. The bar is pivoted at one end at the bottom. It is pivoted or hinged at the bottom. A 200 Newton load of object is hanging from the top. Now we have a 200 Newton force. The question is, find the tension exerted on the cable so that the system is in a state of balance or equilibrium. So how do we determine the tension? We determine the force exerted on the cable for this system to be in equilibrium. What are the force components exerted here? The first force is the load of the object, it's 200 Newton. And the other force component is the weight of the object itself, the bar itself. It is 100 Newton. And here you have a bar, and the bar has length L. This force is exerted at this point, meaning from the pivot at a distance of L. This is a pivotal point, okay? This is a pivotal point. And the weight which is acting here due to the load, due to the mass exerted here, is at a distance of L from the pivotal point. And the weight of the object, or the weight of the bar, is 100 Newton. And 100 Newton for a uniform object is exactly found at the geometrical center. Meaning, you have L, and it's found at exactly L over 2. The distance from this to this is L over 2. And the cable is found at exactly 3/4 of the length L. It says at 3/4, almost 0.75 meter from the pivot is found to be here. And the angle theta is given from horizontal. It is 37 degrees. So how do we determine or how do we apply the conditions of equilibrium? Well, to find this or to solve this, first, what are the force components? The first force component is 200 Newton due to the load, and here you have a weight, and the weight is actually 100 Newton. It says 100 Newton. Here you have 100 Newton, and the length from pivot to this is L. Here you have a tension acting vertically upward at this point. Therefore, the first thing that you should have to use is how to apply the second law of rotational motion, or the second conditions of equilibrium. And the second conditions of equilibrium states that the net torque on a given pivotal point should be 0. Meaning, clockwise torque must be cancelled or counterbalanced by counterclockwise torque. Here we have a clockwise torque. Let's assume that this is a pivotal point. This object tends to act on this direction, meaning it tends to rotate clockwise. The weight of the object itself, the weight of the bar, tends to act clockwise again. This tends to act clockwise, this tends to act clockwise as well. Now the question is, there is a tension T on the cable and that tends to act counterclockwise. So counterclockwise torque must be balanced by clockwise torque. So the summation of net torque must be 0. The summation of torque acting clockwise must be equals to the summation of torque which are acting counterclockwise or anti-clockwise. So we know that torque tau generally given us force F times R times sine theta. This should be the way that we should have to express for torque, where theta is the angle between the exerted force and R. R is moment arm and it's always measured from the pivotal point. In this case, let's try to see the force which are acting clockwise. The force which are acting clockwise are, the first force is the load. The load is 200. 200 times the distance from this to this is length L. Okay, length L. And then here you have an angle theta. And that angle theta is given to be sine 37 degree. This is sine 37 because here you have an angle 53. Okay, angle 53. So that if you project this, it's 90 degree here, so that we can find 37 degree. These are the torque which are acting clockwise, plus the other torque which is acting clockwise is the weight of the bar itself. It has its own weight and it's found exactly at half of the length. For a uniform rigid bodies, their weight is exactly found at the center. So we can multiply the weight times the length is 1 over 2 L. So 1 over 2 L, and the mass of the bar is actually 100 Newton. So 100 Newton times, again, the angle between, here we can take the angle between the moment arm and the force which is the weight of the bar is 37 degree. Again, we can use 37 degree. So these are the force which are acting clockwise. Okay, these are the force which are acting clockwise. And the other force which are acting counterclockwise or anti-clockwise is the tension T. Here it says, let's back again. Here it says this is acting 37 degree, and this angle are 53 degree. Okay, this is 53, this is 53. So 53 degree plus 37 degree, it gives you 90 degree, exactly 90 degree. So the tension is acting 90 degree. Here is the tension T. Actually, it seems more of, sorry for my drawing. Anyways, this is 90 degree, okay? Should be perpendicular to this one. So it is 90 degree. Theta is 90 degree. We have 37 degree plus 53 degree gives us 90 degree. Then this is a force which tends acting counterclockwise. Okay, it's acting counterclockwise. Therefore, the net torque which are acting counterclockwise, the tension T itself, and it is 3/4 lengths from the pivot times sine 90. Sine 90 is actually 1. It gives us 1. So that's 3 over 4 L. Here you have length L, and here you have commonly length L. Here you have length L, here you have length L. Commonly you can cancel out and find the tension T to be 280 Newton. You have the tension T. Therefore, with this, it's possible to find tension. It's possible to apply the second conditions of equilibrium. The second conditions of equilibrium is rotational equilibrium, and it's always emphasis on the torques. You have to put always, if there is a rigid object, there will be a pivotal point. On that pivotal point, the net torque should be 0. That should be the way you should have to think. And the net torque, that's are acting clockwise and counterclockwise must be balanced. Now here one example. So to find it says there is a bridge, okay, and that bridge is 50 meter long, and the mass of the bridge is found to be 800 kilonewton, and it is always on its geometrically center. Okay, the net weight of a given body is given to be exactly at its center. And there are two supports here. Here we have support A and support B. These two bodies must resist those force. And there is another car or truck, and its truck is 200 kilonewton, and it's acting downward. 200 kilonewton. The track is found at 15 meter from one end. From this end, it's found at 15 meter, 15 meter. And the bridge itself is 50 meter long, 50 meter long. So the question is, what are the force in kilonewton on the bridge at the points of support A and B respectively? So to solve such kind of problem, always you have to be very clever in drawing free body diagrams. What are the force components exerted on this object? The force components are the force due to the track, the force due to the bridge itself, and there are two supports here. Therefore, you should have to draw the free body diagram like this. Here you do have the bridge, here you do have reaction force on the support, call it RA, the reaction force on support A, and there will be a reaction force on support B. Okay, and there is also a force which is acting downward, the weight of the truck. And exactly at the center, we'd have the weight of the bridge, which is 800 kilonewton. Now the question is, find the reaction force at support A, here it's support A, and support B. And it is 50 meter, totally 50 meter. And here from this to this is 15 meter. 15 meter. So what shall we do? The first thing is you should have to choose a pivotal point. Suppose you are trying to find the reaction force at point A. If you are trying to find the reaction force at point A, you can choose pivotal point at point B. If you are trying to find the reaction force at point B, you can choose point A as pivotal point. Let's say that point B is a pivotal point. Okay, if B is pivotal point, what are the forces acting here? There is an upward force due to the reaction at point A, and it's found at 50 meter from point B. The other force is there is a weight of the truck, which is 200 kilonewton. And the other force is exactly at the center. We have the weight of the bridge, which is 800 kilonewton. The bridge is found exactly at 25 meter. And the track from point B, always you should have to take from point B or from the pivotal point. From this to this, actually from this to this is 15 meter. So from this to this it should be 35 meter. Okay. Therefore, this should be the way. Therefore, what are the forces which are acting clockwise and anti-clockwise from the pivotal point given here? Here you have a pivotal point. Reaction A is tending to rotate this object clockwise. Okay. Whereas this object tends to rotate the bridge counterclockwise. Always counterclockwise and clockwise are relative. Relative to what? To the point that you take as a pivotal point or hinge point. Therefore, this is a hinge point. I should have to take from this point what are the forces acting clockwise and counterclockwise. RA is acting clockwise like a watch, and those two components are tending to rotate it counterclockwise. Therefore, the law it says the summation of net torque should be the summation of torque clockwise is equals to the summation of torque anti-clockwise. What are the forces acting clockwise? Like a clock. RA times the distance from this to this is 50 meter, 50, and sine theta. Actually, the angle between the moment arm and the force are perpendicular degree, so sine 90 gives us 1. This is the only force which tends to act clockwise from the pivotal point. And these two are acting counterclockwise or anti-clockwise. Therefore, we should have to add these two. What are the forces acting counterclockwise? The weight of the truck. The weight of the truck is 35 meter away. 35 meter. And here you have the angle to be 90 degree. We don't need to use sine 90. Sine 90 is already 1. Plus, we should have to add, because both objects are tending to act counterclockwise. The weight of the bridge times 25. Okay, this should be times 25. Sine 90. Sine 90 is actually is 1. Sine 90 is 1. Therefore, weight of the bridge times 25 and weight of the truck times 35 and reaction A times 50. Actually, the only thing that we didn't know is the reaction at point A, because the weight of the truck is 200 kilonewton times 35, and here the weight of the bridge is 800 times 25 times 25. Therefore, reaction A is 50 times reaction A times 50. So the only quantity that we didn't know is reaction at point A. So we can determine reaction at point A multiplying these two and adding over dividing by 50. This is where we take, if you are trying to determine reaction at point A. To find reaction at point A, you just use point B to be your pivotal point. But if you want to the reverse way, I need to find the reaction at point B. If you want to find the reaction at point B, we can take point A as pivotal point. Meaning, like this. You can choose this to be pivotal point P. The force acting, if this pivotal point, the force acting upward is reaction force at point B. And here we have the weight of the bridge and the weight of the truck. The weight of the truck is exactly at the center, so that here you have the weight of the bridge. The other force or the other weight acting here is the weight of the truck. The weight of the truck from the pivotal point is found at 15 meter, and it is 200 kilonewton. Actually, weight of the bridge either from this point it is exactly at half, and it should be 25 meter. And this one should be 50 meter, so that you can determine, again, applying the second conditions of equilibrium. I hope you have found good concepts. You can solve it by yourself. Therefore, this is all that I have got for today. Students, next time we'll try to see about the property of bulk matter, unit 8. So we'll see you then.